take system responses and signal spectrum. How to do it in MATLAB environment. Okay, today I will be turning into using MATLAB. So if you have it already installed, this is a good time to check it also that it works. But still, it's not totally required to use MATLAB today. Thursday it will be essential, but today's exercise can be done also easily with the Octave. Okay, so basically the questions for the exercise today is the first one is to determine the system parameters. You have done similar system analysis before on the second exercise. And then the second question is about the stem plotting the first 12 values of the impulse response and define or determine if the system is infinite impulse response or finite impulse response. After that, plotting the frequency response if the sampling rate is given 11 or 25. And then from that picture, phase response picture, you should be able to see if it's a linear phase or nonlinear phase. Then zero pole plot. And then basically from that, you should be able to determine what is where the system has highest attenuation. Plotting the group delay. Then sixth one is scaling the system for unity gain at passband. That was pretty easy actually. Then generating again some sound sample, 1.2 seconds long, chirp signal. Wow, okay, chirp. And then random noise. Give it some random noise. And so on. And calculating the spectrum of the last 2048 points, not the first, but last ones. And then spectrogram. Then filtering the sound sample with the filter of this system defined on the first question. Quite nice package. Okay, so let's see. Now let me start the MATLAB somewhere. I have it. Oh, there it is. And I hope it works. This license number. Does it? It's always the guessing if it's getting the. Yes, it got the. It uses a campus license in Metropolia in Finland, so I'm using this one over the internet using virtual private network. Okay, so MATLAB, does it work? Yes, 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 yes. How about here? Yeah, excellent, excellent. So it works just like Octave, but this is the original. It doesn't crash anymore. It hasn't been crashing for the last 10 years. Before that one, it was a pain in butt. But they rewrote the whole code about 10 years ago. And after that, it has been quite stable. Okay, so basically, it has more stuff than the Octave, including lots of toolboxes. And basically, typing VER gives you what toolboxes are there. Most important toolboxes are the DSP system toolbox, signal processing toolbox, and then what was the something else. Fixed point designer, yes, yes. Okay, good. Let me see. I don't see my. Where's the command history? All right, let me put my command history there, for example, so you can see the what I'm typing here. So, command. Let's see what I was going to do. Yeah, I'm confused. Let me. I'm not starting from the same point as you on the exercise, just because you will be learning some new stuff. The where I am actually going to start is I will be just setting some zeros and poles and define the system by that. So basically, if I have zeros, for example, here, this is one of my favorite systems. So the angle is 3/4 pi. Then I have this location of poles at 0.5, 0.5 J, and 0.5 minus 0.5 J. Okay, so those are the locations I have: Z1, Z2, P1, and P2. All right, so for the MATLAB, I first go and define the zeros and poles. And from those information, I go to the system coefficients A and B, or B and A. Okay, so zero location. First zero location is actually on unit circle, so it's exponential of J times 3/4 times pi, like that one. And this is my first zero location. The second zero location is actually complex conjugate of the first one. And the vector for zeros is Z1 semicolon G2, since you have to actually show these vectors. If they are system coefficients, then it's a row vector, but if it's a zeros and poles, then it's column vector. Okay, 1 by something, or this is 2 by 1 vector, since these coefficients are always that way, and the special points are this y vector. Why? Just because. Okay. Poles location, I can also just do it something like this. Everything is scaled by 0.5 times 1 plus j semicolon 1 minus j. No, 1 minus j. There. That's another way of generating these values, either Cartesian or the polar coordinates. And you can plot these zeros and poles using z-plane. Okay, using z-plane, if you have the system coefficients, it will plot the zeros and poles, or calculate the zeros and poles and plots them. If you put there directly these column vectors, then it just plots those on the z-plane. There we go. There we have it. So looks almost as good as my picture there. Okay. Z-plane. Nice thing about MATLAB is actually you can dock these things and put them. I think that you can put it somewhere here, just like that, and make a big mess out of this the setup. And you can always go back to the standard layout. Oh, default layout at any point. Okay, Z-plane like that. Next step, actually, now we have this system. I need the system coefficients derived from the zeros and poles, meaning I need the polynomial coefficients defined by zeros. Those are the system coefficients B. Simply command poly. So poly of a variable gives the polynomial coefs of, or actually from zeros or roots. Yeah, that's the roots. I think that's the mathematical expression is roots. Okay, yeah. So those are the polynomial coefficients for the B. So I can actually now start writing the defining the what is that? Difference equation from that one part, but I still need the other part, which is the A is the polynomial coefficients defined by poles. There. Nice, neat numbers. Quite easy to calculate. Although that square root of 2 is kind of, you can only do a approximation when you're doing it on a small microcontroller. Okay, so those are the polynomial coefficients, and now the corresponding difference equation would look like something like this. We have y of, this is just comment, y of n equals, okay, x of n plus 1.4142 times x of n minus 1 plus x of n minus 2. And then we have coefficients from the polynomial, the AA. The first term here, this is the scaling factor for y of n. And this one is the the rest of those are the coefficients for the feedback term. And remember, when you move those on the other side, then actually this would be not minus but plus y of n minus 1. I'll continue on the second row, and then minus 0.5 times y of n minus 2. So that's the difference equation based on those polynomial coefficients or system coefficients. Okay, now we can do some stuff with this one. For example, determine if the system is infinite impulse response or finite impulse response. Yeah, that was the next step. FIR or IIR. The brute force way. First we take some index vector, for example, from -2 to 8, something like that. This is my region of interest. Then I make the delta function, simply saying double, nn is 0. So this is the impulse function. And the impulse response is then let's see, IR, impulse response, is, actually it's also HH, impulse response. Filter, BBAA, when the input is the delta function. That's impulse response. Seeing is believing. let me take new figure. That probably goes somewhere there. Let me dock that one on my small figure window here. I know I should have much bigger screen or more screens here. Okay, new figure and plot the stem plot my NNHH. So stem plotting the impulse response picture. There. This is a second order system. The order number comes from the highest delay, and my highest delay is 2. So it's second order system. Or actually my order number, you can see it from here. 2 zeros, 2 poles, meaning second order system. So the question is then, is there any non-zero values after second order delay, which is here? When the index is 3, we have a non-zero value already there and more to come. So this system is infinite impulse response system. IIR, since there are non-zero values after highest order delay. There, good. That's done. So we can actually plot the impulse response and also determine if it's infinite or finite impulse response system. Good. The next step was to, well, let's see, frequency response. For frequency response, we need some sampling rate. Let's think of this as a, say, sampling system for data. 2000 Hertz is a wait a minute, what was your function generator sampling rate? Was it 2000 or 4000 on that exercise? 2000, 4000, 1000. Okay, let's use that one. See, 1000. Good. Actually, you could already start writing the code for the this system. Second order system. It's very simple. You have this is the difference equation, and here it doesn't really matter if it's optimized or not. You just need to have a subroutine that has local memory for the input and output, the previous values of input and output, the hard-coded coefficients. Okay. Maybe I'll show you how I would do it. But anyways, that's a say some measurement system, typical sampling rate. On this exercise, you have one of the standard audio rates because it's audio signal. Fs equals 1000, and now we can plot the frequency response. Frequency response is simply Frech BB AA. And then in how many points it's evaluated, 1024 is just fine to get some detail. And then we have the sampling rate. I think that is how it works. But I can always take a look at the function browser. Okay, returns endpoint frequency response vector H, or actually, yeah, there. That's the way I'm using it. Frech with parameters, and n is the how many in how many points it's evaluated, and so on. That's fine. How do I get this one out of the... okay, there it goes. Yeah, so double-clicking a function and right-clicking, you get basically help for editing. Okay, compared to Octave yesterday, this is a professional tool. If you ever need to do some signal processing in real life in company, ask if they have the MATLAB. If they don't have it, then it's somebody else's job. And change the employers since they are saving on the wrong place. It's like putting, if you go to a construction, if you work on a construction, you would expect the this builder, your boss, to give you some power tools like jackhammers and that kind of things. You don't bring those from home. Same thing here. But anyways, so the frequency response. Let me put that one again on its own figure. Okay, so it looks like that. Wow. Wait a minute. I have second order system. So it has 5 multiplications for additions. I had that also compared to 4-point running average filter, which has, well, 4 multiplications, 3 additions. But look at the performance of this filter already. It has some signal gain. So as a filter, we must also do some work for the gain. But anyways, the difference between the stop and attenuation, okay, there it is actually, minus 12.61, and then passband gain 18. So it's 30 decibels of stop and attenuation already, compared to 12 dB of that useless running average filter. Much better performance. Okay. However, this is IIR filter. IIR filters never have linear phase response, as you can see here. So this is not linear, so it's non-linear. If it was linear, then it was straight line. Just a angle K there, and otherwise straight line. So we are losing some on the phase response, but on the other hand, we gain a lot more on the amplitude response. Okay, that goes also into my figure safety box. Good. So frequency response I can plot. And by the way, when you have this frequency response, or the frequency sampling rate defined, then this is physical frequency here. And basically, where is the, okay, let's take it off again. The highest attenuation is actually at 374.5 Hertz. Not exactly. The exact frequency would be when you take the 0 location and say angle of Z, for example, at first Z, exact frequency of max attenuation. Okay, that's normalized frequency here, which means that we can always divide it by 2 times pi and multiply with sample rate. Yeah, 375 Hertz exact. So that's the maximum attenuation frequency. Okay, good. Let's take a look at what is the next part. Does the system non-linear? Yeah. Zeros and poles I already plotted, but okay, let's plot it again from this system coefficients, just to be on safe side. Okay, so this is the my original zero pole plot. Whoa, it is so small. Oh, okay. I undocked the whole thing. Let's put it back. So new figure, Z plane, ZZPP, well, BBAA. There. Looks like the same. So I started with the zeros and poles and calculated the system coefficients, and yeah, I got the same back. That's nice. What did I prove there? Nothing. Other than it's still the same thing. Okay, group delay. Group delay, how do I get the group delay? Let's see, docuport GRP delay. Let's see, does it find? Yes. Oh wow, I'm so good on finding this help. Okay, you saw the quick help of the MATLAB window, but there's also this full help. When you write doc group delay, for example, it gives you the instructions how to use the group delay function. And actually, it's the same way you can use the this frequency response. So, okay, that's fine. Maybe I docked that one too. Where do I dock it? Maybe there? No, it's not good. No good there. Okay, so group delay on new figure delay. And again, the same parameters. We have just this system coefficients like that. And then, for example, 1024 points. And then we have sampling rate. This shows the group delay. And as you can see, this group delay shows that we have one sample delay for DC. Makes kind of sense since this is second order system. So for if DC component goes without much of the filtering, then basically you get usually the middle filter. Half of the filter is the normally the group delay. But okay, when you go closer to the this higher, so on that angle, practically around this angle, you have the highest group delay also. So the samples are actually delayed by 3 time steps already. Yes, so there's a quite big variance on how long the data takes to pass through the system. Let me put that one on that figure window there. So, okay, what did they do? Okay, that's the amplitude response, group delay, zeros and poles. Okay, and then let's see what's next. Scaling. Scale the system such that it has unity gain and passband. We do it engineering way, meaning brute force. Who needs mathematics when you have brute force? Okay, so scaling to unity gain, meaning that, okay, where do I have that? Here I have it. So the only problem with this amplitude response is here, if it's also filter, it's not a good idea to have too much gain on the passband. Optimally, the filter does just filtering, not amplification of the signal. It's done separately. Otherwise, you will end up in big mess with all the scaling and such kind of things on the system. So for the filtering, it should do just filtering, meaning you need to get the maximum of this filter output as 0 dB, meaning 1, gain 1. And that is easily done since I just, let's see, I have the frequency response. No, okay. Bigger frequency response. The frequency response, a function is returning if I let it to return. Where is function? There we are. So it returns actually the H and B returns endpoint frequency response, meaning the complex frequency response. And some HW there, but well, who cares about that? There we go. So it actually returns some values. Let it return the frequency response HEXP and also some the frequency axis information there. Okay, so the first one is the complex frequency response. The second one is the frequencies it was evaluated. There. If we divide or rescale, for example, the coefficients B with this value, we will get what we needed. So practically what we are doing will be okay, H of Z, this BK on ZT minus K, 8K times ZT minus K. We multiply this one by the 1 over max gain. So this rescales the whole thing. We cannot touch these since that one, the first parameter A0 is always 1. We have to keep it 1. And we cannot, of course, change the other ones. We can only scale the whole thing if needed. So it means that practically we go and divide BK parameters with this one. Or if this was a real system, then you would probably just scale the filter out. But on MATLAB for unity gain, BBU equals BB divided by maximum of absolute value of HEXP. So amplitude response is the absolute of this frequency response, and then we take the maximum value. So this is brute force scaling. Figure BBU AA. There. Unity gain on passband. Good. There we go. So basically those are the examples from 0 to 6. Interesting. Generate sound sample, which consists of the 7th question actually is it's quite simple. I will just give you a couple of hints on the existing functions. Let's take the document. Documentation. and let's search for chirp. Chirp signal. What the heck? Oh, this is so. Let's see, chirp. Functions. Wave for generation. I'm just trying to find. Okay, that's the okay. Now there's the one problem with the help of MATLAB is actually there's the same keyword is in so many places. It's hard to find what is the what you should be using. What you should be looking is this description of a function. So chirp actually requires generates samples of linear swept frequencies cosine signal at the time instances defined by array T. And basically it starts from frequency 0 and ends to frequency 1. T is a time vector, so here, and T1 is the end time. So that's how the chirp actually works. So for example, let's see, how does it sound like? Chirp. Now I'll show you something. How to make longer sample time vectors. Auto indexes is nice for smaller amount, and if you need to have fixed amount of data points, but if you want to have fixed time of data points, then you can still use, for example, like this from 0 with the time step of 1 over fs. Okay, I will use different frequency sampling rate here to 1 second. So this actually, if you have 2 semicolons, it means from with a step to something. And chirp signal actually sounds like chirp. I have T. F0 would be, it was really obnoxious. You can start it from 1000 Hertz. And then at 1 second, it's 2000 Hertz. Then it really sounds really awful, which is good. 44.1. Okay. There. So this is just an example of how chirp works and how this kind of chirp sounds like. Yep. Ooh, what was that? You didn't have the end frequency. Yeah, I know. This is so much fun. Yeah. Yeah, this is so much fun. Okay, so that's my chirp signal here. Let me just do some. So this is my chirp signal for fun. That's how you can make the longer samples. Okay, how to add some noise? Actually, there's a function for that one too. Let's see. Help. How was the other one? Signal to noise ratio. No, going noise. Noise. How did it go? I don't remember. Noise component, noise to measurement, noise sounds. Rand n signal to noise ratio of how was it that I can add some noise to this signal? Input arguments. There is a shoot. Why I don't see it here? There was a way to add a noise, certain amount of noise to the signal, but I don't see it now here. Signal processing toolbox, correlation model signal modeling, maybe here. Parametric modeling, autoregressive, no. Signal processing toolbox again. Signal generation. Okay, functions. No noise. Yeah, one big problem is that if you know what you are looking for, but you don't quite get the right keywords, you cannot find anything from here. So I'll do it the old-fashioned way. So I can actually again calculate the variance of CC. Variance of CC is variance of CC, and then do, for example, if my signal to noise ratio was, let's put it minus 3 dB. And then actually I can calculate the variance of noise. It was, okay, 10 to power of something, right? 10 to power of minus SNR divided by 10. Was it something like this? I don't remember. From yesterday. Maybe. We'll see. So that's the variance of noise. Does it make sense? Yes, it actually does make sense. See, the variance of CC is about 1. No, it's not 1. It's okay. Variance of noise, and then basically noise is random numbers for size of that CC times square root of variance of noise. That's how I scale that. So I have variance there for the noise and variance for that one. Okay, blah, 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 blah. What I'm blabbering here. Yada, yada, blah, blah. Let's check it that it's actually that one. Log 10 of variance of CC divided by variance of noise. No, I'm missing something here. Oh, yeah. Right. Minus 0, or was it 10 times that? It's about 10 times too small. I'm missing here something, but well, I'll figure it out later. So I have some noise in my system. I have minus 0.3 decibels of noise. Okay. Okay, but anyways, I have some noise. So my noisy CC is CC plus noise there, sound CC no, and FS. Yeah, some noise. Good. So this is just my sample. Try to do better work on the on the adding the right amount of noise. This is not correct. Okay, so when you have some noise sample or sound sample and you want to make a filter for that, when you need to do the spectral analysis of the signal. No doubt about it. So let's go and do some spectral analysis. I take subsample from CCNO from first 1024 samples. yeah, the little sampling rate was probably a little bit low on that one. Oh. Okay, so I will take just small portion of this since I have 44,101 samples. It's a bit quite big and usually quite useless to make the Fourier transform of a whole package. And as we can hear, it's more important to make the spectrogram than the Fourier analysis of the signal. But let's do a simple spectrum calculation, the old-fashioned way. Calculate the Fourier transform of sample. Then basically we know that power spectrum is this Fourier transform multiplied by the complex conjugate of Fourier transform. Okay, again, this is the operation, cell-wise operation, not the vector operation, but the cell-wise. Okay, this is the power spectrum, and this is full spectrum, meaning that it actually has all the data from 0 pi to 2 pi. But we need only this part, top part. We need only half of that signal. So my interest is actually in this from 1 to 513. Why 513? First element has the DC component, and then plus 512. That's where the sampling rate divided by 2 is Nyquist frequency. Region of interest. Okay, now I have the indexes. Next thing, this is power. You want to plot it in decibels. dBPYY is 10 times log of 10 of PYY in dB. Then you also want to probably know the physical frequency axis, which is quite simple. FF equals int minus 1 divided by 512. That actually, well, actually I can do it 1024 times fs. So we use the same scaling as anywhere else. So basically, the indexes are giving the basically the division from in how many points the full spectrum from 0 to 3 sampling rate is divided in 1024 points in our case. So it's linearly mapped. So this is my frequency access information. And now we can plot it. New plot. Plot, not stem anymore. Plot x is ff, and the other parts dp, pyy, and but only the ins values. There. That's the power spectrum in decibels. There are also some functions that gives you the power spectrum estimator on MATLAB, but try to find yourself. Actually, Google might work better than this document browser. Seriously. Okay, so we have that chirp signal actually is producing some. Wait a minute. Why I have not FS? I have wrong FS here. Sorry. I hard coded it in 44.100. That was my FS. All right. So figure. There we go. Better. Okay. So here we have the signal is starting around 990 hertz. How come it's supposed to start at 1000? Why we have some spectral component here at less than 1000? Any guess? The spectral resolution. Okay. FF2 minus FF1. That's the spectral resolution. Spectral resolution is about 40 hertz. So on this graph, there we have the some spectral components. Actually, also 990.5 hertz. That's because that's the bin that happened to be there with this multiple of the spectral resolution. Okay, when you're doing a spectral analysis, you really want to pinpoint the what is the exact frequency. Then you need to have more points when you calculate the spectral the spectrum of the signal. On the other hand, when you are designing filters, this would be quite fine for design purposes. For example, if you want to make a low-pass filter that cuts anything above 5 kilohertz, then you would basically use that to find, okay, you need at least some amount of this stopband attenuation. But that's a topic for tomorrow or this afternoon. It depends. Tomorrow you will have regular hours with somebody else, right? Have? Tomorrow you have some choir. Choir? So, okay. Briar. Okay, good. Excellent. Then you can show him that, okay, this is how we do filters nowadays. And he says, ha ha. All right, good. So Yeah, spectrum. This is single spectrum of the very beginning of this data set. More interesting would be to see how about a spectrogram. Now I need to actually take a look at the current spectrogram since days. Oh, not there, not there, not there. Find in page, close that one. Contents, documentation, home. Spectrogram, signal processing, wireless communication, signal processing toolbox, spectral analysis. Okay, they are the periodogram. Actually, I think they are calling it also periodogram. Maybe. Let's see. No, these are actually the spectral responses. Just yeah. Okay, good, good. So let's go back to the spectral analysis and find the finding page spectrogram. Huh? What? Again, they have changed it and something, right? No, no, no. Oh boy, big mess. Oh wow. Yeah, there. That looks like a spectrogram. P spectrum. Wow. New function for me. I started using MATLAB. Then it was called spectrogram. The spectrogram function was called spectrogram. Next step, suddenly the same function was called spectrogram. Now it's P spectrum. But anyways, that's nice. I will just use that one with okay, frequency limits. Maybe I just use it up to here. X is my CC. No, and sample rate is 4.4100. Let's see what does it do for me. Yeehaw! See. That's nice. That's a spectrogram. On Octave, you would call spectrogram. But on here, we have actually the color-coded image of how the frequency is changing over time. So the power in dB is actually on color code, and that yellow line starts from 1 kilohertz and ends at 2 kilohertz in time from 0 to 1 second. So basically, based on that one, you can start thinking, okay, that looks like noise. Let's filter it out by defining a low-pass filter which starts somewhere in here, about 3 kilohertz or so. So we have the full data for this one. It doesn't affect on the signal itself, but cancels as much noise as required from this topic. Okay, but that's not today's topic or this topic. So this is the spectrogram. Ha. Nice. Okay, now the question is, I have those filter coefficients, although the filter, I have just 1000 hertz, the sample rate there. Well, let me fix the sample rate for the 4.100. Just for fun. And to confuse you, this was way too clear this far. Okay, and my frequency response. Okay, I'll just put this one here. Frequency response for my system BBAA. Wait a minute, why doesn't? Okay, there we go. So frequency response of my filter would on this frequency sample rate actually would be like that, and we can now actually use this filter to filter our data simply by saying YY equals filter BBU AA and then CCNO filtered data. And show again the power spectrum or spectrogram of the signal like that. So that's what happens with this filter for the data, which is quite obvious, right? Yes. Quite obvious what it does. Where's my if my filter amplitude response is the left hand side, there is that notch around 1.1. What was the frequency? That notch is at about 16.5 kilohertz, which is right here. So that bluish line here means that the power has been gone down on the pass on the stop band. Okay, so this is a low pass filter, and it should suppress some of the noise. But let's hear if it suppresses it so that we can hear it. So this is the original sound, and then filtered sound. Any change? Other than the later one is a little bit louder. Not much. Not much. Not a good audio filter. You can still hear the noise. Okay. Anyhow, let me put that one back here. And take, oh boy. What I did today. All right. I started from this system. In your case, you will start from a block diagram and define the parameters from there. I started from 0 pole plot, just to make a point. And basically, this system, I calculated the filter coefficients using the poly command. What is my poly command? Here, it's somewhere in here. In my, let me go to the cancel. Let me make Control A and then create script that I can show you something. All right, so I actually define these zeros and poles from the graph here. Then I make the Z-plane to verify my design. There we are. And next step, what I did actually, I calculated these coefficients. Maybe I should save this one for fun. This is the exercise. Exercise 3. Okay, verified it. Then I calculate the polynomial coefficients, which basically gives me this corresponding difference equation. Then I did the impulse response using the filter command. Actually, there is also a impulse response you can calculate from int_c from MATLAB. But on the other hand, you don't need so many functions. It's the same thing as you do the impulse function first the same way you did it yesterday, and then just run it through this system, and then basically stem plot this impulse response, which look like where's my figure? Just there. Looks like that. And from impulse response, you can see when you look data after the highest order delay, which is the highest order delay is 2. This is a second order system. So if there are any data after that one, non-zero data, then it's IIR. Okay. Okay, that's extra. And then group delay, that was GRB delay. We had the frequency response somewhere. No, not that one. That one, frequency response, calculate the frequency response. Well, wow, what happened? Oh, great. Okay. Oh boy, this is so confusing too. Frequency response, that's just freaks, and then group delay. What else I have here? Well, the same frequency response. Then I have, okay, spectrogram. Let me close those so I confused myself. So all the tricks what are needed to reproduce what I did will be on this one. Okay, then I played with this longer time sampled vectors like in here. So basically, generate the time vector, the sample time vector. So from step to then sound, and then sounded the chirp. Tried it out, and so on and so on. And finally, I basically calculate the spectrogram. Wow. There was a difference on the sound. The second one sounded like from early Star Trek movies. Right. Okay, good. So that's all the hints for today. You can start working on the exercises, and actually it's now 12:38. Just about lunchtime, right? Take the lunch break, come back, work on the exercises, and hopefully I can already start the theory part of for the next, which is the filter design. Yes, and actually, that's a curiosity. When we have these filter coefficients A and B, A is that one, B here. It wouldn't be that hard to work on embedded system code anymore, since think of your sampled system. So you have some sort of sampler there, probably a timer interrupt, right? And then on every single timer interrupt, you go and generate the next value for those sinusoids, right? It works something like that. Okay, so instead of generating the, or in addition to generating that one signal, you can actually also have, say, function. I think there are floats on that processor. Yes, yeah, float data type is allowed on STM, right? Does it have the coprocessor there, or is it software float number calculations? I'm not sure either, but it has lots of power. All right, let's think it's a float. Okay, float, and then we have this filter, which takes only one single float number, which is x. There, okay. Inside of the filter, you basically, okay, you have the filter coefficient somewhere. So b, okay, float, b vector has three values. B is 1.0, 1.4142, and 1.0. Those are the values on filter coefficients. Actually, this is constant, table of constant. So const float a, again same thing, 1.0 minus 1.0, 0.5. Inside of here, what you need is actually something that corresponds into your difference equation. Where's my difference equation? Yes, difference equation. You calculate the output. Float. Oops. Y. Y equals that one there. X. Times B0, or B0 times X plus B1 times, well, X1. X with the time delay. So basically what you need to have here is a local memory for the previous values, X1, X2. And what can be used, what kind of variable actually does not disappear between the function calls? Static variables. Right. So you calculate this using the previous values every time, and before you return, you actually just update it so that those previous values are okay for the next round. It's quite straightforward, but the general idea is like that. So you have this coefficient table for the B and A, then you just have one single signal value. The current signal value goes into this function, and you calculate the output using this difference equation, and you have these static variables to save the previous values for X and Y. And before returning, you there basically do something like that. Y2 is Y1, X1 is X, Y1 is Y. Update these previous values, which are static. Okay, so that's the second order filter. Very simple to do. And then you just need to have the engine to call this function for every single the time step. Okay, good. So now we can go to have some lunch.